We'll get started. In our previous video, we talked about Navier-Stokes equations, how to derive them. We also talked about viscosity, the property of the fluid. We talked about the relationship between the stress and strain rate discovered by Newton. We also talked about three-dimensional relationships between the stress and strain rate developed by Stokes. We also talked about Stokes' hypothesis. We talked about the property of the viscosity in gases and liquids and how it changes with temperature. We also talked about something called Stokes' hypothesis. Finally, we talked about Newtonian fluids and non-Newtonian fluids. So a lot of material was covered in the previous lecture. Navier-Stokes equations are highly nonlinear, therefore it's very hard to solve analytically. So there are a few exact solutions that we could still solve, and we can use those to get an understanding of the physical behavior of Navier-Stokes equations. In our course, the second homework set is basically based on these exact solutions, extension of these exact solutions. So let's get started. So we are going to go to the exact solutions of Navier-Stokes equations. These equations are developed, as you know, a long time ago, 175 years ago. Only a handful of exact solutions exist. That's because these equations are nonlinear. So it's a common practice to solve using computers. CFD, computational fluid dynamics, is nothing more than numerical solution of Navier-Stokes equations. There are lots of software available at Georgia Tech, freely available to you, such as Fluent, that you could use to solve viscous flows on a computer. So let's get going. So we are going to look at a very simple class of problems called parallel flows, which are primarily flows that are going from left to right in the x direction, not a lot of vertical motion. So we are going to talk about a very long flat plates in the x direction or a very long tube in the x direction. In such a long tube, infinitely long flat plate or long tube, it's unlikely that we'll have x derivatives, because if you have even a small derivative over an infinitely long distance in the x direction, it'll build up into a big change in the u, or big change in the v, big change in t. In reality, infinitely high velocities or temperatures, which is not possible. Therefore, we will assume that the flow has got zero gradient in the x direction. So that's what we will be assuming. So here is an example of two types of parallel flows that we will be considering. One is a flow between a flat plate. The other one is flow through a pipe. These flat plates are very long in the x direction. Sometimes you need something to cause the motion. In 2D, for example, if you move the top plate from left to right, that's enough to create momentum in here. How about a pipe? Pipe is a stationary object. This is the same wall of a pipe as this. In between there's fluid. So in this case, you would need some kind of a pressure gradient to pump the flow from left to right. Therefore, we allow pressure gradient to be non-zero in x direction, but we do not allow any of the pressure gradients. You may ask, wouldn't this become infinitely large? Yes. Therefore, every few hundred feet of a pipe, if there's a pressure drop, you will need to raise the pressure. That's why if you look at the water systems, every hundreds of meters, they will have a water pump which raises the pressure to keep the fluid moving through the pipe. So here we say homework number 3. One of the homework is just a X-file project. So in our course, homework number 2 deals with the applications of these equations to some practical problems. So let's go to the conservation of mass we had developed earlier. We are going to take a steady flow. Therefore, d by dt is time derivative is gone. We are going to assume incompressible flow. Therefore, rho will be a constant. In a minute, we are going to set the x derivative to 0. That means we'll only have things varying in the y direction for 2D problems or in the radial direction for axisymmetric flow, such as a flow through a pipe. So conservation of mass, if the x derivative goes to 0, this goes away, you get only this quantity. Now it could be very easily integrated, dou by dy of rho v equal to 0. That means rho v could be either a function of x or rho v can be a constant. It cannot be a function of x because if anything is a function of x, it will have an x derivative, but we cannot have any non-zero x derivative at all. Otherwise, the derivative will build up over a long distance, infinitely long distance. So we assume that rho v is just a constant, therefore rho v is a constant in this case. Likewise here, rho times r times v is a constant in that case. Now, if rho v is a constant, that means since rho is a constant, v is a constant. Look at our 2D flow between two flat plates, like the one that Newton considered. Flat plates are solid pieces of metal or structure, so no flow can cross that particular surface. So the v component of velocity is 0, both for the top wall and the bottom wall. Therefore, the only constant that will make sense is 0. Therefore, v equal to 0 in the case of a flat flow between flat plates. If you look at a flow through a pipe, rho r v equal to constant, therefore v equal to constant. But in a tube, you cannot have any v velocity in the top boundary, which is the r equal to capital R, or this boundary, which is also the boundary of the same tube. So the only constant that we could support the boundary condition at this walls is 0. Therefore, in both the flow between a flat plate and also flow inside a tube, we get v component of velocity equal to 0. We only have u component of velocity. That's why we call it a parallel flow. Only u components are present. Therefore, we call the flows parallel flows. So the parallel flow between the two flat plates is called the Couette flow. Flow through a pipe is called a Poiseuille flow. These were the Frenchmen who had studied it. So we are going to first start with Couette flow, then we'll go to Poiseuille flow. Now, let's say that one of the flat plates is held fixed. The other plate is moving at a velocity v, like Newton did. Let's say we also apply on top of it a pressure gradient dp dx. The two flat plates are separated by distance h. So if dp dx is 0, we get Couette flow. If dp dx is a non-zero, positive or negative, doesn't matter, we get a Poiseuille flow. So this is the flow we are going to consider between two parallel flat plates. So this is a top plate. Top plate is here. Bottom plate is here. This is at y equal to h. This is at y equal to 0. This plate is held fixed, therefore u and v are 0. This one is moving, therefore u is non-zero, but v is 0 because nothing can penetrate the boundary. So let's solve the governing equations for this case. We have already solved the conservation of mass, shown that everything has to be parallel to between the flat plates. So let's solve the u momentum equation. So we are going to do steady flow, therefore the time derivative vanishes. So the first term goes away. Infinitely long plate, therefore x derivative goes away. V velocity is 0, therefore this term goes away. So we are left with only the pressure gradient that we may have, which is dp dx on the left side. On the right side, we just have d tau xy by dy. Why does this go away? Because nothing can vary in the x direction, because even a small non-zero value over an infinitely long distance will build up into a finite value. Think of a Peachtree road race. When you're near the Peachtree Battle area, the ground starts sloping up. So the runners are struggling uphill. they don't notice the gentle rise of the road because you have to go maybe 100 feet to climb up about 1 or 2 feet. But by the time you reach Piedmont Road, Piedmont Hospital, what you call a Heartbreak Hill, you have climbed hundreds of feet, because when you look back, you see the runner's head behind you. So sometimes they call it a Heartbreak Hill because of the excess work that you had to do to climb up or run up this particular hill. I call it a heartache hill because there are a lot of McDonald's and Burger Kings on both sides, which may not be good for our health. Anyways, now we have dp dx on the left side, some pressure gradient. We have d tau xy dy. So we can integrate it in the x direction. Since this is not a function of x, this will just become, when you integrate it, tau xy will become dp dx by dy, possibly plus a constant. The constant, we call it a. Now tau xy according to Stokes is mu times du dy plus dv dx. V is 0 because of the parallel flow, so this goes away. So you get mu times du dy equal to this quantity. Take the mu to the other side, 1 over mu. Call it a over mu as a new constant a. Integrate again. You'll get u equal to, this y will become y squared over 2. A will become ay. Then you'll pick up another constant. So you pick up 2 constants. So you need 2 boundary conditions. You need one at the bottom wall, one at the top wall. At the bottom wall, u is 0 when y equal to 0. The top wall, u equal to capital V when y equal to h. So when u equal to 0, y equal to 0, if you put 0, 0, 0, then it follows that b equal to 0. If you put u equal to capital V when y equal to h, then you can solve for a, then you get this particular relationship. Notice that it's got a second derivative of y, therefore it's a parabolic profile. So the velocity profile, if you plot it with respect to y, it'll be a parabola. So in Couette flow, dp dx is 0, therefore this term goes away. So you just get a very simple linear velocity profile. But in Poisson flow, dp dx is non-zero, therefore you get a parabolic profile. So in Couette flow, dp dx is 0, so you just get a very simple linear profile. Tau xy will become mu times du dy. So if you take du dy, this is gone because there's no pressure gradient. It will be mu times v over h, which is exactly what Newton had found. So we have recovered Newton's stress versus strain rate that he found empirically by analytically solving the flow between the 2 flat plate where the top plate is moving. Now let's look at the pressure gradient. Let's say that there's a pressure gradient, but the top and bottom plate both are at rest. Then you'll get a parabolic profile. It'll be 0 when y equal to 0. It'll be 0 when y equal to h. It'll be maximum when y equal to h over 2 in the middle. This is a negative number because y minus h is always negative. Therefore, pressure has to drop. dp dx has to be negative. We need a favorable pressure gradient. That means the pressure is dropping along x to produce a positive flow from left to right. On the other hand, if you have an adverse pressure gradient, that means if this is positive, pressure is rising with x, this is a positive number, then because this is a negative number, u will be backed up. This is what happens when you have a blockage. Flow wants to back up because the high pressure, the blockage, pushes the flow backwards. Now let's take a look at the flow through a pipe. Similar to our flow through a channel or a flat plate between 2 flat plates, except now it's got a little bit more complicated. du dx is 0. You get 1 over drv dr equal to 0. X is along the axis. R is the vertical direction. Again, very, very long pipe, so x derivatives go to 0. The only exception is you need some kind of a pressure gradient to pump the flow through the pipe. Otherwise, the friction will bring it to a complete stop. Therefore, we assume a constant pressure gradient, dP dx, is being applied. So integrate the conservation of mass. This goes away. So you get d by, there should be an r here, rho rv. Rho is a constant. So rv is a constant. So v equal to constant over r. At the axis of the pipe, r equal to 0, you cannot have an infinitely high velocity. So the only meaningful velocity that we could have is zero v component of velocity. Likewise, at the walls of the pipe, v is 0. Therefore, this constant has to be 0. So the only meaningful solution we get from the conservation of mass, there should have been an r here, like we showed in the earlier slide. There's an r here, rho rv. Rho drops out of the picture. So v is 0. Now we go to the u momentum equation. Many terms disappear. X derivative goes away. V component of velocity goes away. X derivative goes away. R component stays. So we get a pressure gradient pushing the flow from left to right, balanced by the viscous stresses pushing the flow in the opposite directions. When these two balance, you get some kind of a steady flow. So let's integrate this. Keep this term on the left-hand side, the pressure gradient. This viscous term on the right-hand side, multiplied by mu. We're going to flip it, bring the right side to the left side and the left side to the right side, just for the sake of integration. So this is the viscous term, this is the pressure term. Now take the r to the other side. Now tau xr is mu du dr. So tau xr is mu du dr. So take r to the other side, integrate it. You get r du dr. Mu, we can bring it to the other side. Then when you take this r to the other side, when you integrate it, you'll get r squared over 2. Anytime you integrate it, you pick up a constant of integration. Now bring this r to the other side. So this will become r. This will become c over r. Integrate it one more time. You'll get r squared over 4 because you have an r. R squared over 2, you already have a 2, so it'll become 4. C over r will become c log r plus d. So in homework number 2, this is your starting point. You will be starting with this and applying the boundary conditions. For our pipe problem, when r goes to 0 at the axis of the pipe, logarithm of r 0 is minus infinity. So u will become infinitely negative. That's not a physically feasible solution. So we turn off the c, therefore c drops to 0. Therefore, d has to be kept. Now we choose d so that when r equal to capital R at the solid wall, u goes to 0. So set u equal to 0, set r equal to capital R, then you can solve for d. Then the final profile that we get is a velocity profile that is shown here. Again, this number is always negative. Therefore, we need a pressure drop in the x direction, a favorable pressure gradient, to push the flow from left to right. If you have an adverse pressure gradient, that means if dP dx is positive, because this is negative, u will be in the negative direction. That means the flow will back up. That's what happens when you have a clogged pipe or when your toilet clogs. Now we can do a volume flow rate. Since you have ur here, just multiply by 2 pi r dr is the area of a circular ring. Take multiple rings, integrate from 0 to capital R, all the way from the axis, all the way to the edge of the pipe. Then you get this is the mass flow rate. We notice that the mass flow rate is proportional to r power 4, not pi r squared. So if we have one very large pipe, it's much better because the radius is power 4 than two small pipes of the same cross-sectional area. That's why in hydraulics, waterworks, they try to use large pipes to bring the flow very close to where it's needed, like in our neighborhood, before splitting that large pipe flow into smaller pipes that go into the individual houses. Now the pressure drop determines how much volume flow rate we are getting. If you have a high volume flow rate, you need a high pressure drop. If you have a low volume flow rate, you need a low pressure drop. So the volume flow rate is directly proportional to the pressure gradient. So this equation is good for laminar flows. In turbulent flow, there is a higher friction loss because of turbulent mixing, which brings the high velocity near the wall. Therefore, the velocity gradient, the change in the velocity per distance, is very, very high in viscous flow. Therefore, the very high skin friction. Therefore, we would need higher pressure drop in rough pipes in turbulent flow, whether it's a large diameter or a small diameter. We could also compute the average velocity, take the volume flow rate, divided by pi r squared, then you get an average velocity. The average velocity is proportional to the pressure gradient. So how about the skin friction at the wall? Tau, this is Stokes relation, V is 0. du dr, all you have to take a derivative of u with respect to r, then apply r equal to capital R. So when you do that, then you will get this as the shear stress of the wall. So shear stress of the wall is proportional to the pipe radius and the pressure gradient in the laminar flow. These are all for laminar flow. So we have completed some exact solutions of Navier-Stokes equations. Unfortunately, there are not very many exact solutions. Anything beyond that, you have to go to computer. That's why we have CFD, computational fluid dynamics, and software such as Fluent. So we have to simplify the Navier-Stokes equations before we can proceed further. That's the subject of our following sequence of lectures.